Oh, hi, everyone. I think it's about the time. So we're going to have our last but also very exciting talk given by Professor Xiao from University of Washington. The title today is Lattice Reconstruction, Piezoelectricity, and Topology in Twisted MoTE2. Let's just give a welcome to Professor D.
All right. Oh, thank you. Thank you very much. And it's also super convenient to arrange my talk right after Xiaodong's. So we've heard this really exciting talk from Xiaodong, where you can see that the twisted MoTE2 is a really truly fascinating system that can exhibit a lot of interesting correlating and topological states. So you notice that I've changed my title, the title of my talk a little bit to better reflect content of this lecture. Is that I will actually mainly focus on the single particle part of this material system and talk about how do we model the system and what kind of surprise we learn along the way. So basically, given a kind of a physical problem, we try to understand it. As a theorist, the first thing is let's write down the Hamiltonian. The interacting part is typically very simple. It's just a plain old Coulomb interaction. It's hard to solve. But here, what's really interesting is actually the single particle part, or namely from the band structures. So here is the let me see. So here is the outline of my talk. I will first give you a sort of overview of the search for the zero field fraction quantum Hall effect, mainly from the theory point of view. And then I will give you a very brief introduction about the basics of the twisted transition method like cogenites, its crystal structure, its band structure, and so on and so forth. And then I will show you the main results of our recent work, which is the twist angle dependent topological Moiré band structure. And finally, I will show you that actually at certain twist angles, there's a higher Landau level physics and the non-abelian states. It's actually possible. In fact, through Xiaodong's talk, he already gave outline of my talk. So just a rerun of those. So this is the quantum Hall effect. In Xiaodong's talk, he didn't show you this plot. Now I'm showing you this one. So you can see that the quantum Hall effect is basically characterized by the quantization of the Hall resistivity, and at the same time, the vanishing of the longitudinal resistivity. And this is actually one of the very first example of non-trivial topology in condensed matter systems, right? And we also notice that there's really, you have to apply a very strong magnetic field, 10, 20, 30 Tesla to really see this phenomena. And in fact, the sample quality has to be really high. There's a reason why people spend so long to develop high quality samples. But in terms of technological applications, to maintain a strong magnetic field is always a cumbersome thing. So then the question was really that, okay, how can we get rid of this magnetic field? Can we realize those quantum Hall effect at a zero magnetic field? And so in fact, this question, I think it's being asked almost right after the discovery of the integer quantum Hall effect. So the very first step is this very famous paper from Lattice and the collaborators, the TKNM paper, where they actually showed that if you just using very standard Kubo formula, the Hall conductance can be written as the integral of the so-called barrier curvature, and which is this integral here, right? And then this actually can be turned into an integration along the boundary of the Brownian zone of a vector potential, then which has to be quantized. And this is called a integer. So in Lattice's original paper, what they actually considered, that's when I was a student, when I first read the paper, what they consider is a two-dimensional electron gas with a very strong magnetic field, but also with a periodic potential. So then if you apply periodic boundary condition, the wave function we are talking about here is actually magnetic Bloch bands. So this seems to leave the impression that this is only applicable when you have a magnetic field. However, we know that in a real experiment, there's always disorder, which then you don't have transition symmetry, and in addition, you always have interaction. And in addition, back when they wrote the paper, the quantum Hall effect is understood in terms of the Landau level. There's no periodic potential, right? So then the question is whether we do we really need a periodic potential? So all these questions has been addressed in a subsequent paper from Chern, Lattice, and Yunxi Wu. And what we showed is actually using a very clever trick. It's called the twisted boundary conditions, that they can put the two-dimensional system on a torus, and then you can insert these two flux through the holes of the torus. And what we show is that in the thermodynamic limit for any gapped system, the Hall conductance has to be an integer. And there's one exception, which is that if the Hall conductance happen to be a fractional, then this implies that the ground state has to be degenerate. Again, it's actually on a torus. And later on, the degenerates of the ground state, the relationship between the degenerates and ground state, and the ground the topology of the manifold, the Nivang, has been explored by Xiao Wen, and which really leads to the birth of the so-called topological order, right? And so a very interesting thing in their paper is that even though I think in their mind that they are looking at a quantum Hall effect, but if you look at the derivation, there's really no magnetic field needed, right? So what their conclusion is a very robust one, that as long as it's an insulator, whether the gap is due to a single particle gap or due to some interaction gap or mobility gap, as long as it's an insulator, the Hall conductance must be quantized. But there's one caveat, because 0 is also an integer. So this really didn't say much. So this really, until then 3 years later, in a famous paper by Duncan, and he first wrote down this very simple tight banding model that to show that indeed you can have a quantum Hall effect at a 0 magnetic field. So basically the gist of this model is that you consider electron hopping on a honeycomb, and then Duncan designed some really clever magnetic flux pattern such that the total flux across the entire honeycomb is actually 0. So there's no Landau level physics. However, those flux will actually open a gap at the Dirac point, and which then give you an integer quantum Hall effect. Even though this is called a toy model, and later we know that it's kind of really close can be realized in graphene-like system if it turns on spin-orbital interaction. So this is really the very first example that in a modern language, it basically shows you that if you have a Bloch bands that with non-zero Chern number, then it can really mimic the Landau level physics. So when the band is fully filled, you should have a quantized Hall conductance. So then this is the sort of theorist's dream that's written back in 1988. And very interestingly, to realize this phenomenon, it take an unexpected sort of long way. So this is 1988. We have a toy model in the broken time reversal symmetry for the spinless fermions. And then 17 years later, King and Mali decided to add an electron spin to the model. And this gave us the celebrated King-Mali model, basically describe the physics in honeycomb-like system with time reversal symmetry. But this kind of enlarging of symmetry is not just a theoretical breakthrough, but it also enables us to look for more common materials. So there are way more non-magnetic materials than magnetic materials. So just 2 years later, and this three-dimensional topological insulator has been found with this beautiful Dirac cone and shown in APAS. And finally, you can make this into a thin film and dope it with magnetic ions to break time reversal symmetry. And then eventually, so that's after almost 25 years, right? Eventually, this integer quantum Ernst Hall has been realized. Okay, so that's the sort of the story of the integer quantum Hall effect. So the question naturally is then what about the zero field fractional quantum Hall effect? So as it turns out that if you really look at the Landau level, a Landau level not only provides a non-trivial topology, but it also quench the kinetic energy of the system. Okay, so in that case, then the interaction really becomes the dominating factor in a physics problem, and the fractional quantum Hall effect can manifest. Now, if you truly believe this kind of analogy between Bloch bands and the Landau levels, then naturally, if you have a Bloch bands with non-zero Chern number, but also it's also flat, then there's a possibility that it may mimic the Landau level and also be able to host the fractional quantum Hall effect at a zero magnetic field. So in the year 2011, there's a bunch of papers that appeared. So people have start talking about this flat Chern band, and also in this paper and those two papers, the exact diagonalization study has been performed to really confirm that indeed the flat Chern band can host the fractional quantum Hall effect. Okay, so realizing this, as I said earlier, also been talked about in Xiaodong's talk, is that it really opened the door for a lot of interesting possibilities. And I think the most impactful one, or the one that can get you funded, is the possibility to do topological quantum computer. Okay, so now the simple story, right, is very simple. If you can find a flat band, and if the Chern number is 1, then there's a possibility you can realize this interesting state. So the next immediate question is that where do we find this kind of a material system? So before we talk about the TMDs, I just want to mention this paper that I've done a long time ago, is that we actually proposed that the transition metal oxide, just in a very simple perovskite system, could be that system, right? So you can see that if you think about a perovskite, it has AbO3 chemical formula. So this green atom is a rare earth. These red ones are the transition metals, and the yellow ones are the oxygen. And because the d orbitals is the active orbital in the system, if you just look at the transition metals, they just form a very simple cubic system. Okay? And what I need you to do is actually look at the system from the 1-1-1 direction. So if you look at it from 1-1 direction, they are just a triangular lattice. And if I have a bilayer system, it's basically become a honeycomb, but it's a barcode honeycomb. The A and the B sublattice of the honeycomb is on different layer. Okay, and very simply, if you just plug in, just assume you have d orbitals hopping on this very simple cubic structure, but it's a 1-1 bilayer, you will see the band structure indeed give you a topologically non-trivial bands. Yes. That's my hope. Yeah. So basically, you can regard this as a d orbital version of the kinematic model, right? And what's interesting about this is that unlike the kinematic model, because it's basically pz orbitals, you look from the top is isotropic. The d orbitals are highly anisotropic, and those actually hopping can give you actually extremely flat band, as you can see here. And so our proposal is that if you dope into the system, then it can give you a fractional quantum Hall state, as we showed here. So unfortunately, this system is because perovskite is intrinsically a bulk cubic structure, and the cliff is probably not possible, and so grow this system in the 1-1 direction. There has been some effort I'm aware of, but it's extremely difficult. But I want to throw that idea out there, because then this is truly a fractional changeless state at atomic length that actually naturally give you a larger Coulomb interaction and potentially even higher temperatures. Okay. So with this being said, so where else can we find a flat Chern band? This is where when the twisted transition metal cogenites come into play. Okay. So let me actually just go through some basic facts of this material system. This is a three-dimensional rendering of the unit cell. You have the transition metal sitting in the middle, and then on the top and the bottom layer is kind of sandwiched by those carbogen atoms such as selenium, sulfur, and tellurium. Now, if you look at the side, okay, so this is a side view, and it's very obvious that inversion symmetry is broken. And this is actually a very, very important symmetry property of the molar layer. And in addition, you will see that it actually still have mirror Z symmetry, right? So which means that if you turn on the spin orbit interaction, the spin Z will still remain a good quantum number. Now, if you look at the system from the top, you can see that you can see a honeycomb-like structure. The red is the transition metal, and the blue is actually those two will overlap when you look at it from the top. But anyway, it's give you a sort of honeycomb-like structure. And if you look at the band structure, it's also very, very similar to graphene. You have those band edge located at the corner of the hexagonal boson, but with two very, very important differences. The first one is that because the inversion symmetry is actually broken, so that's actually a gap opening at the Dirac point. And so this single particle gap is about 1 eV to 2 eV. So it's pretty large in terms of the energy scale we are talking about in terms of milli eV. And in addition, in the transition method of Hodgenites, the active orbitals are the 4D and 5D orbitals. So the spin orbital coupling is extremely large. And coupled with the broken of inversion symmetry, it will lead to a very large spin splitting at the valence band top. So you can see that this is spin up and spin down. And this energy scale is typically on of 100 millieV to 200 millieV. So that's actually extremely large splitting. And then finally, because we have inversion symmetry, we also have time reversal symmetry. So when you have spin down in one valley, then you have spin up in the other valley. So in this case, the spin and the valley, they are coupled. So those are very, very different from graphene system. Like in a graphene system, spin and the valley, they are independent degree of freedom from each other. But in the TMD, because of the spin valley coupling, it sort of gives you the simplest system you can study. Okay. So then, as you can see from the experiment, the most interesting physics really happens when you dope the valence band. And because this is really, as I said earlier, this is roughly on the order of 1 eV. This is roughly on the order of 200 MeV. So you can ignore all those connection band and the valence band below. Just look at the valence band top. Okay, so that's the basic information about the monar layer TMDs in terms of their structural and electronic properties. Now, next week we consider how do we form a bilayer. That's another scenario when graphene and the TMD are different because of the inversion, breaking of the inversion symmetry. You see that when you have the two layers stacked together, you have the so-called H stacking and R stacking. So what's H stacking? H stacking is basically you have two identical layers, but the top and the bottom layer are rotated by 180 degrees. But for the R stacking, those two are aligned in the same way. Okay. Again, they in graphene, because graphene has a C6 rotation symmetry, there's no such difference. But in the TMD, even before you do the rotation, there's already two different stacking possibilities. Now, what's the big deal here? So the big deal is that, remember that in my TMD system, I have the so-called spin valley coupling, right? So each valley has a specific spin component. Now, this is a top layer. This is the, oh, I should have rotated this. This is spin down. Okay, so it's a good thing I have a different color. So basically now this is the top layer, this is the bottom layer, because you have rotated by 180 degrees. So therefore, for the same valley, the spin orientation are opposite. So then in this case, the inter-layer tunneling is actually forbidden. Okay. Now, if you consider the R stacking, then this is when the top and the bottom layer, so they are aligned together. So you can still have interlayer tunneling. So that's a huge difference. So that's why in the experiments, all the experiments done for this R stacking, because we actually needed that interlayer coupling to have some non-trivial topology. Okay. So with that being said, let's actually focus on R stacked twisted TMD homo bilayers. So you can just do a little bit twist. You can have this beautiful moire pattern. And on this pattern, I want to draw your attention to some of the high symmetry stacking point. And this is actually very important for our later on discussions. So first, those black dots. So this is called stacking, because if you look at a side view, you have this metal on metal or carcogen on carcogen, right? And then this green dot and this red dot is called the XM and MX, because now you have metal on carcogen and a carcogen on metal. Okay, so those are the three high symmetry stacking points. Now let's actually look at the symmetry of those stacking. So you will notice immediately that due to this, even though the monar layer have a mirror Z symmetry, but for those bilayers, due to just the way they are stacked, obviously the inversion symmetry is gone. And in fact, the MX and the XM point, they are related by a mirror Z reflection. Okay, so now if you want to think in terms of electric dipoles because inversion symmetry is gone and the mirror symmetry is gone. So actually, out of plane dipole is symmetry allowed, and also they must have opposite dipole. But if you look at the MM stacking, even though the inversion symmetry is gone, we still have the mirror Z reflection. So in that case, if you can only have an in-plane dipole rather than out-of-plane dipole. So that's the very, very important information we're going to use later. And finally, we can also look at the overall point group symmetry of the system. So those are basically 2 layers of the honeycomb. And if you look at this, you realize that it has the symmetry point group of D3. So it have a threefold rotation symmetry and also have a C2Y axis. If you do a C2Y, what you're going to do is you're going to flip the two layers. So those are all the symmetry that are respected by the system. Okay. So now with that being said, we're at a stage that we can finally start writing down the Hamiltonian. So again, we first begin with the molar layer. As I said earlier, we're going to throw away the conduction band and all the band below the top valence band. And then now we're going to rotate this a little bit. So once you do a rotation, you can see that still we can group the top and the bottom layers together. We have valley spin up and valley spin down, and they are still separated by a very large momentum transfer, which allows us to consider those two valleys separately. So then you can see that this would be the simplest Hamiltonian you can write down. It's very easy to understand. So first, because I have a homo bilayer, so naturally you need a layer index, you need the top layer and the bottom layer, right? And then the kinetic energy here, because the Moiré period is much larger than the lattice constant, so I can use the effective mass approximation. So naturally, the kinetic energy is just given by h bar k squared over 2m. You might notice that I have this kappa plus and a kappa minus. That's because the two layers are rotated against each other. So when I count the Dirac points, so the Dirac points of the top and the bottom layer are shifted by a certain amount, and that's what the kappa plus and the kappa minus is. So we're done with the kinetic energy part. So for the rest, we can just stick all these deltas in there with some constraint. The first, the system has to be Hermitian, and secondly, it has to respect the symmetry we mentioned earlier, which include the D3 point group symmetry as well as the translation symmetry at the Moiré wavelength. So once you do that, then you can actually very easily write down the form of the Hamiltonian. And you can see that for this top and the bottom layer, it can be written in terms of the Fourier expansion in terms of the reciprocal Moiré wave vectors. And this is the intralayer Moiré potential, and this is the interlayer Moiré potential. And here, following what Anna McDonough did, we only do a first harmonic expansion. So that seems to be really a very simple model. Okay, so then with that being said, we need to determine, this V, W, and psi. Those are the parameters that used to characterize the system. So in Anna's paper, what they did is actually very simple. Is that you can go back to this picture, right? So you can then locally I will have a local stacking. You can basically do a calculation at those local stacking and extract the parameters at a local value, then apply the symmetry operation. Then you will obtain those parameters. So from those very simple calculations, what they find out is that this system actually supports topological bands. So why is that? So there's a very simple reason to understand this. As I said earlier, the effective Hamiltonian is basically 2x2 Hamiltonian. So you can definitely you can pull out the kinetic term, and then for the rest, they just form a spinor representation. Therefore, you can define a spin texture. And this spin texture is actually a Skyrmian lattice in real space. Right? So as we mentioned earlier, this is the mx, this is the xm point, and due to symmetry. So here, this layer pseudo spin can only point in out of plane. So in this figure, the color means the z component, and then these little arrows means the winding of the in-plane component. Okay. So now you can see that even in terms of topology, we have a very simple kind of real space understanding, is that we are basically looking at an electron moving in a Skyrmion lattice, but it's a pseudo spin because here is a layer index. And we are all aware of this topological Hall effect. When you have an electron moving in a spin texture, it will experience a Barry phase, which is given by the span of the solid angle, this S1 dot S2 cross S3 type. And so basically now we see that if you look at a twisted transition metal Alcogene light, one of the sort of intuitive way to understand it is just to think about electrons moving in a spin texture. And so then it's no wonder that the band structure can have some kind of non-trivial topology. And one of the things I also want to mention is that because we are talking about a triple product of the three spin, right, and the three component. Now, if you flip one of the component, then the topological lambda would have to change. Okay. So with that being said, so Alan have done the calculation of the topological band structure. You can see that at a small twist angle, which in their calculation is about 1 degree, you can see those Moiré mini bands. And most importantly, you have the two very flat bands, and they have opposite Chern number -1 and 1. And that's why some people will say that the twist TMD actually realized the Kim-Mali model. But I will show you that that's a twist angle dependent statement. Now, if you go to a large theta, so when you go to large theta, it means that the Moiré unit cell becomes smaller. But if you just think about it in terms of hopping between the Moiré cells, the hopping becomes larger. So therefore, at a large twist angle, you can see that the band becomes more dispersive, and also the Chern number go from -1, 1 to -1, -1, and 2. Okay. So anyway, so the point is that if you just think about the twisted TMD homo bilayers, it really gives you a topological non-trivial band structure. And of course, so here, why the bands are really flat. So unlike graphene systems, here you can just think about the electrons being trapped in the Moiré potential. Right? So when you go to a large twist angle, they are far apart, hopping becomes small, so the band becomes flat. And then also, I want to emphasize that what's shown here is in one of the values, say value k, you also have a value -k, which is a time reversal copy of the system. So when you think about the whole system, I really have a time reversal invariant system. So without interaction, I'm talking about is kind of a quantum spin Hall insulator here. Okay, and finally, so the physics now it becomes something like this. You have the k value with spin up, you have k prime value with the spin down, and now you can start to dope the system, right? And then you can ask yourself that what are the possible interacting state? Sometimes those two values will form a coherent state. This is the inter-value coherent state. But sometimes it would prefer a value polarization. And in that case, if you dope the system, it becomes fully value polarized. And because my Moiré band also have a Chern number -1, then you should have a quantum Hall insulator. So that's sort of the basic picture in terms of how we think about those interesting interacting phenomena that has been seen in the experiment. And now, of course, we have flat band. We have it also topological non-trivial. Then the question is whether a fractional quantum Hall effect is a possibility. So about 3 years ago, Kai San and Shi Zhenling have done this just a very simple ED calculation, and they find the following phase diagram, right? What they predict is that, okay, as the twist angle changes, so indeed, there's a FCI state. It's also fully value polarized that can be stabilized in the phase diagram, and roughly it's at 1.440 degree. Now, if you go to higher angle, then this state will be destroyed. So at least that's their prediction based on the first harmonic expansion. So now everything seems to be set up. The only thing needed is Xiao asked a student to spend 200 hours in the lab making a device, right, and see what's going to happen. But there are in fact two puzzles. The very first one is that the experimental twist angle is about 3.9 degree, right? But in the phase diagram that I just showed you earlier, the prediction is 1.4 degree. You can say, of course, the experiment theory cannot always match, right? The theory shouldn't be too arrogant. But a 1.4 degree and a 3.9 degree, that's actually a huge difference, right? That's a 2.5 times smaller in terms of the Morey potential. So something is probably wrong with the original modeling. And the other more interesting thing is that at the same time, we also saw a paper out of Ben's group, and what they showed is that they look at the twisted WSE2. So this is the same like a strata formula measurement, right? Different technique, but it's same physics. Now, if you notice is that their twist angle, the slope is actually different. So the opposite of slope means the opposite sign of the Chern number. This is also very puzzling, because if you think about the electronic structure of WSE2 and MoTE2, they are essentially the same. Okay, there are some details in band dispersion, but the large feature, which value corresponding to which spin, they are all the same. So why do they have different sign? But what we notice is that, I don't know how those guys did it. They actually did it at a twist angle of 1.23 degree. It's very hard to make a sample, I know. So then Xiao sample is at a 3.9 degree. So then, which makes us think maybe this difference is not due to the different material, but it's really due to different twist angle. So then they said, so with all these motivations, we started looking at this more carefully. Okay, so what we found is that the lattice reconstruction is actually extremely important in how to describe the system properly. So, we all know that if you put this van der Waals header structures to a twist, you can see that there's all kinds of beautiful pattern, and all this including very strong lattice reconstruction. So the physics is actually very simple, right? Because if you do a twist, then there are all kinds of stacking. And there are some stacking which are energetically more favorable. Some stacking cost more energy. So naturally, the system want to grow those stacking with lower energy. But once you grow, then you will have deformation. So it's gonna cost the elastic energy. So then that's a computation eventually give you this lattice construction we've seen here. And it turns out that the MoTE2 is a much, much softer material compared to graphene. So even at a 4 degree-ish, we still should expect a very large lattice reconstruction. And indeed, this is what we see in our DFT calculations. So unlike a previous calculation, we literally put all those like roughly 1,000 atoms into the computer, just ran the code. And now you can see that here is this in-plane lattice relaxation in a Morey cell. Those arrows indicating the displacement field. And shown here is the out-of-plane relaxation. Basically, there's an interlayer distance is also changing. And I drew a line card. You can see that at the MM point, you have the largest interlayer distance. At XM and MX, you have the lowest interlayer distance. It's also very easy to understand this just by looking at the structure here. Because for MM, you have a carcogen sitting on top of the other carcogen. They are both negatively charged. They don't want to be too close together. But for the MX and the XM, you have a cation sitting on top of a lion. So naturally, the distance can be a little bit smaller, right? So everything we've done, so really check out with the intuition. And finally, you can look at the band structure. So you can see that shown on the left is a large-scale DFT where the lattice reconstruction is considered. And shown on the right is actually the band structure without any lattice construction. So the first thing you notice is that, look, this one has a very large dispersion at a 3.9 degree. But this one has a much, much flatter band. And in addition, you see that even the Chern number sign is different. That's really interesting. Remember, one of our motivations is to try to explain why there's a sign change, right? So with all being said, so then we can sort of we can sort of fit the band using this Continuum model, so the red dot is actually from DFT calculations. The black curve is from fitting, and you can see from fitting, indeed, we've seen that once you take into account of the lattice relaxation, the Morey potential becomes much larger, right? 8 milli EV becomes 20 milli eV and 8.5 eV becomes 23 MeV. So just shows you that that's a flat band. Yes. Yes, yeah, thank you for that question. Those are from the gamma points. Because if you look at the band structure of the TMD across the Brillouin zone, the band edge is at a K point, but the gamma point is very close in energy. So those are those we have verified it's from the gamma points, so we can throw it away. Oh, no, I mean, if you can just think about the band dispersion, if you think about graphene, you draw a curve, say that's the K point, right? But in TMD, you keep going to gamma point, the bands come back, you have sort of a secondary pop at the gamma point. And they are very close in energy to the K point. Now, if you fold them back, so you're going to have two sets of Maury medium band. One is from K, one is from gamma. So those are the gamma bands. Yeah. All right. Thanks. By the way, if you have a question, feel free to let me know. Okay. So now we claim that lattice relaxation is super important, but still we need to verify whether this is really true or not, right? Unfortunately, we already have a experiment, so that's going to be our benchmark. Yeah, go ahead.
Important, right? So what's the like compared to the renormalization of the bands through the lattice relaxation? What's the scale of the renormalization of the van der Waals?
So I guess like the variation of the interlayer distance should give you a indication, right? So it basically go from 7.4 to roughly 7 in terms of the interlayer variations. Yes, yeah. It's actually super important. That's actually create a lot of confusion and the things. So anyway, so now we have this new set of parameters, so we can test to see whether this actually, better reflect the experimental observations or not. So basically, what we've done is that now we start adding interactions. That's as a standard interaction. That's the Coulomb interaction. And because usually in the experiment you have a top gate and a bottom gate, so you have a screening. So this tanh term here is to characterize that screening, and this D is the gate to sample distance. Okay. So then once we have that, the very first thing we did is that we basically run a ED calculation on 3x4 lattice just to verify whether the system is fully value polarized or not. And you can see that at both 1/3 thinning and 2/3 thinning, so the fully value polarized ground state is actually preferred. So that's actually good news, right? Then once we know that the electron going to be just limited to one value, we can actually just focus on one value. And the advantage is that we can run a ED calculation at a larger lattice site. So here is a many-body spectrum at on a 4x6 torus. So first is that if you look at the spectrum, you immediately notice that first there's a gap, and also there are 3 degenerate ground state. Okay, that's sort of the hallmark of the fractional quantum Hall state on a torus. And we have also done this flux insertion, which allows us to calculate the many-body Chern number, which to confirm is indeed 2/3. And once those calculations are done, you can also look at the whole phase diagram. So this is the phase diagram. The horizontal axis is the twist angle. And here, this is we just changing the dielectric constant. And here we are changing the gate to sample distance. And the color here just indicating the size of the gap. So you can see that with this new set of parameters and the optimal angle to observe this FCI state has been moved to roughly 3.5 degree, which is very close to the experimental value. So this really gave us a confidence that the lattice relaxation is actually very, very important to correctly capture the single particle band structures. So I also want to caution you that what we did is a so-called single band projection. Just doing the exact diagonalization study is extremely computational intense. So recently there's a paper from Barnevik and the Nicholas group to show that if you include a second band, it actually would affect the stability of the FCI state. And in that calculation, then the 1/3 state would be gone, but the 2/3 FCI state still still survive. So the band mixing could be a very important factor when we consider the interacting physics. Okay, so we can also do more testing and compare with the experiments. Now, because we are talking about the homo bilayers, so you naturally have 2 layers. Now, if you apply an electric field, it will introduce not just the pushing charges into the system, right? It will give you a potential difference between the top and the bottom layer. If you want to think in terms of the Hotan model, that's basically give you A and B sublattice potential difference. So this becomes a extremely useful tuning knob. And you can see that, so as we increase the gate voltage, and then the many-body gap will gradually goes down, and at roughly 1.2 millivolts per angstrom, the gap will close. So the 2/3 FCI state has been completely destroyed. So on a first thought, you would argue this is kind of expected, right? Because if you apply a strong enough electric field, then the system, as Xiao said, will go from a honeycomb-like structure to a triangular-like structure. The bands will become topologically trivial. Of course, the FCI would be destroyed. However, if you just look at the single particle bands before and after this gap closed, look, here is the single particle band structure at a 0 electric field. And here is a single particle band structure at a 1.39, which is right after the gap close. You can see that there's really not much difference. You know, the band width is about the same. The Chern number is still the same, which means that the single particle bands haven't crossed each other, right? So then why would this FCI state be destroyed? So to just shed a little bit of light on this, what we did is that we then can compute the barrier curvature and the quantum metric distribution in the momentum space. You can see that at a 0 gate voltage, it's actually quite uniform. You see some variation, but not large. But then at the electric field where the FCI has been destroyed, then you see a very large fluctuation, right? So basically, the barrier curvature and the quantum metric, both they are constant for the Landau level. So therefore, the flatness of those two quantities has been, I would argue, heuristically viewed as some kind of signature or indicator of whether it's good or bad to mimic the Landau levels. So I want to stop here because I think there's more to this story, but still, just looking at the barrier curvature and the quantum metric distribution in the moment space, I think it's a pretty good indicator in the numerical calculations. Okay. So now, with all this being said, so what we've done is that we show that if you just do things in a brute force way and include the lattice relaxation carefully, and we should be able to model the system. But what about the small twist angles, right? Remember the calculation we've done is roughly at a 3.9 degree. And you see at a 1.5 degree twist angle, then the Moiré period is about 10 nanometer. And then there will be 10,000 atoms in the unit cell. So if you put it in a computer, it will create right away. So the reason is actually not because you cannot do the band structure calculation, but because when you do the lattice relaxation at each step, you have to perform a full DFT calculation. And usually it'll take more than 100 steps to relax to a minimum. And sometimes you're not even guaranteed you're going to be in a local minimum. So it's just really time consuming and impractical. So that's where the machine learning actually becomes very useful too. So this is really collaboration with my colleague Ting Xiao. So it's actually a really straightforward application of the neural network. So if you think about it, the total energy is a function of all the atomic positions, right? But what we're going to assume that we assume the energy is local. So we're gonna drill a hole, say about 1 nanometer, and then we're gonna consider all the atomic position inside of this. And then we can calculate the total energy at a larger twist angle, say 6 degree, and then that you can easily done within 1 or 2 hours. So once you do that, then our training data is generated by running the molecular dynamic simulation at 500 Kelvin. So the reason is that we want the atoms to explore a lot of parameter space, but I still want them to stay at a physically reasonable space, right? So by running this MD simulation at a very high temperature, we can achieve that. And finally, we can also verify this because the training is done at 6 degrees. Then we can verify this neural network representation of the interatomic potential at 5 degrees. You can see that this is from direct DFT calculation. This is from our neural net, and it really agrees really well. So with the neural network trained, we can easily obtain the relaxation pattern within seconds. All right, so enough about that. So now let's actually look at the result. So now you can see this is the lattice reconstruction obtained from the neural net calculations. And this is at a 3.15 degree at the large twist angle. You can see that those are the lattice. This is the in-plane lattice in-plane relaxation pattern. This is outer plane. And this one is done at a 1.25 degree. Okay. But you immediately notice that here, a very clear, very large domain has been developed. This is the MX and the XM region. They have the lowest energy. Now at a small twist angle, the Moiré unit cell becomes really large. So the system has enough space, so to speak, to relax and to make the domain grow. And now you can see a very clear domain wall that's been developed here, right? But at a 3.15 degree, then you still see some domain structure, but things are much, much smoother compared to the 1.25 degree. Okay, so this is very important. Now, once we have this lattice structure, then we can run the DFT calculation to obtain a band structure. And on the top is the band structure of twisted WSE2, and at the bottom is the band structure of twisted MoTE2. And in addition, we also determine the Chern number by taking advantage of the threefold rotation symmetry. So we only need to calculate the eigenvalue of the wave functions at the gamma and the kappa prime point in the Brownian zone with one caveat. And this Chern number is only determined modulo 3. Okay. Now, with that being said, let's actually look at the band structure. This is for WSE2. So this Chern number is 1. This is 1. Now you go to 1.7. It's 1, 1. You go to 1.54. It become 0, 0. And now if you keep going to the small angle 1.25, it becomes a -1 and a -1. So we need to see the flip of the sign of the Chern number. And this is roughly where Ben's experiment is done. So the sign of the Chern number and also even the second band, I think, agree with your data. Now he's nodding his head, so it's true. Okay, but now let's also look at the MoTE2, right? Now at 3.89, that's where the initial discovery was made. You have Chern number 1 and a -1. Now you reduce the twist angle, so 1 - 1, 1 - 1, 1, 1, 1, and then we'll go to 1.25, the Chern number becomes 0 and 0. Okay. So in fact, when we first wrote the paper, we actually assigned this 1, 1, -2, because remember that the Chern number is only defined modulo 3. So 1 and -2 for us is the same, right? And when you see 2 Chern number 1, just, okay, let's make it the -2 so we can close this manifold. But later we actually performed more detailed calculation based on linear functions and to confirm this is actually 1. Now this is already super interesting because I think before this calculation, even for us, we didn't expect to see this multiple Chern bands, always Chern number 1. Okay? And now that's another difference between WSE2 and the MoTE2 is that you can see in general the MoTE2 bands are much flatter. Okay? This is due to 2 reasons. One is that MoTE2 has a much larger effective mass compared to WSE2. And the secondly is that MoTE2 is actually softer compared to WSE2. So that's a stronger lattice reconstruction. Therefore, the Moiré potential is also larger. So in fact, if you look at this without doing any calculation, you know that across this very large twist angle, we should always stabilize this integer quantum Hall effect. Okay, but why? Why does the Chern number change sign? Why it go from 1 to 0 to -1? Okay, so remember that, as we said earlier, the whole physics is really determined by the Morley potential. And one way to kind of visualizing this Morley potential in our calculation is that you can look at the Hartree potential difference between the top and the bottom layer. So that roughly tells you the Z component of the pseudo-spin skyrmions. Okay, so now let's look at that. You can see that this is at a large twist angle, 3.15 degree. XM is blue, so it's pointing in plane, and MX is red, is pointing out of plane. So that's my North Pole and the South Pole, and it's very regular. And if you do a Fourier transform, you're gonna get the first harmonic would work. Now, when you go from 3.15 degree to 1.7 degree, now you can see that red regions start developing at XM. In other words, the pseudo spin at the North Pole and the South Pole has flipped. Okay, and then if you go to smaller twist angle, then this will keep growing, this middle region, and then eventually it will become the dominating source, right? And all those original blue colors has been pushed to the domain wall. And as we said earlier, if you just keep the pseudo spin texture, doing nothing, but just flip the North Pole and the South Pole, the skyrmion number would have to flip, and then Chern number would have to flip. So this is actually consistent, right? It shows you that as you change the twist angle, somehow this real space layer pseudo spin texture is actually changing. And by the way, we can also look at the Fourier transform of all these Morley potentials. You can see at a large twist angle, indeed, the first harmonic coefficient is very large, so then the second one is small, then it goes to 0. But when you go to smaller twist angles, you can see that, see at a 1.7 degree, the first harmonic coefficient actually go to 0. You really have to go to higher harmonics to capture this pseudo spin texture. So that's another lesson we learned. And we can also look at the location of the wave functions. So shown here are the wave function at the gamma point of the first and the second Morley bands. Now you can see that, so the first band is located at MX point, but the second band is already located at the MM point. And the Chern number is 1, 1. So now if you go to 1.54 degree, now you see that, okay, now if you go to the next angle, the wave function location is the same, MX and MM. But now if you go to the next one, it is switched. So the wave function goes to MM, but then for the second band, the wave function comes from MM to the MX. And this is easy to understand because as we said, right, whenever you have a Chern number change, which means that the band with different C3 eigenvalue has switched. And here, the way the system switch the C3 eigenvalue is by going in different high symmetry point in the Morley-Bernoulli zone. Okay. So anyway, what I'm telling you is that our calculation is consistent with the Chern number change, but I still haven't answered. Oh, here is also a wave function of the twisted MoTE2. So I want to show this because now you can see at a 3.89 degree, the first band and the second band, one is located at, so they are both located at MX. This is only on the top layer. So in the bottom layer, they would be located at XM. So for 3.89 degree TMOTE2, you can think it as a kinematic model. You know, they are really on a honeycomb lattice. But as soon as you go to 2.14 degree, now you can see the MM point becomes super important. Okay, so the tight binding, if you want to develop a tight binding model for each different twist angle, you would have to involve different number of orbitals. So that's the point. Okay, but why? We know that all this, right, change is due to the flipping of the North Pole and the South Pole. It was like this, but as a twist angle changes, it will gradually go reduce, then flip side. So why is this? So now remember that we have visualized this change of the Morley potential by measuring the Hartree potential difference between the top and the bottom surface. Okay, but remember that we are dealing with a real material system, so it's a charge neutral. for a charge neutral system, if you have an electric potential difference between top and the bottom surface, it means you must have a interlayer dipole pointing in the z direction. So where does the interlayer dipole come from? You see, oh, that's very easy because we have been talking about this from the very beginning, right? Because you think about the stacking, you know, the xm will have dipole pointing up, then mx will have dipole pointing down. So there you go. That's why I have those two dipoles. But if this is really the only contribution, then the pseudo-spin would never flip. Because, you know, as you change your twist angle, what you are doing is that you are making the distance between xm and the mx become larger and larger, but the local stacking would always be the same. So the dipole moment only due to this kind of stacking ferroelectricity cannot change. Okay. So there must be a competing mechanism. So where does it come from? Okay, so this competing mechanism is due to the fact that in a molar layer TMD, again, inversion symmetry is broken, which makes it piezoelectric active, right? Because in molar layer TMD, even though inversion symmetry is gone, you still have a threefold rotation symmetry, which will forbid any development of an in-plane dipole. But I have a lot of lattice reconstruction in the system. When you have a strain, you're going to break the C3 symmetry, then a dipole can develop. But the strain is highly non-uniform. So when I have a spatially dependent dipole moment, then that will give you a piezoelectric charge. Okay. So basically you can see that this is the displacement field, and this is the piezoelectric charge. You can see that very interestingly, it has opposite sign in xm and mx. Okay, so now for the top and the bottom layer, the relaxation pattern are opposite. So their charge, their piezoelectric charge are also opposite. So this way we have another source of interlayer dipole. That's purely due to the in-plane piezoelectric charge. Okay, so with this understanding, I can give you a very simple explanation of why the pseudo-spin will flip sign. Okay, so you see that at a 3.15 degree, this is the piezoelectric charge, and because the relaxation pattern varies smoothly, they are mostly concentrated at the xm and mx region, and this is the ferroelectric charge. They are opposite in sign. You add them together, this guy wins. So you have blue here, red here. So north pole, south pole. But when you go to a smaller twist angle, say 1.25 degree, remember that now I have really flat, very uniform domain wall in the middle. So you kind of drive all the string gradient to the boundary of the domain rather than the center of the domain. In fact, you can see that at this corner and the boundary, you have much darker color than the middle. So the piezoelectric charge at the center is being driven away, but the ferroelectric charge sort of stay the same because it's a local property. Now when you add them together, then in the center, actually you have red instead of blue. So that's where the flipping of the pseudo-spin comes from. Okay. So I also want to really emphasize that in a graphene system, because the graphene is inversion symmetric, you don't have this effect. So when you model the graphene, the twisted graphene system, we don't have to worry about this kind of long-range piezoelectric effect. But in TMD, not only we have to, it's actually really crucial. It can flip the sign of the Chern numbers. Okay, so that's sort of the main story. So let me make some remarks. So, you know, there has been several different parameter sets flowing around, and all are obtained from large-scale DFT calculations. And now depends on what you do in your calculation, you could have different parameters, right? So the most important factor deciding the parameter difference is the van der Waals functional. So our group, the Princeton IOP collaboration and the Berkeley team, we all use the DFT D2 just for the expert in the audience. But the MIT team used the scan plus DSC, and this actually caused the largest parameter difference. And also there are some small differences arise due to different packages like VASP, Siesta, Quantum Espresso, but those mainly determine the difference between the gamma and the K and the K bands. But besides those details, There's some general trend I want to make sure the message is crossed. So to capture the band structure accurately, compared to the original model, you really need two things. One is that I showed you that the higher harmonics is actually pretty important. Okay? Just due to the molecular potential is actually varying at a very large, very fast. And the secondly is that in twist bilayer graphene, the parameters are sort of like twist angle independent. But here we see those Fourier coefficient varies significantly as the twist angle change. So you really have to build this twist angle dependence into the continuum model. Okay, so how many minutes do I have? Can I go another 5? 10. Oh, 10, that's wonderful. All right, so now I want to show you that we have the band structure. Then we can think about what are the interesting correlated state we can find. So first, this figure shows you the band width as a function of a twist angle for both twist MoTE2 and WSE2. You can see again, as we said earlier, that for MoTE2, roughly once you enter 3 degree, you have relatively narrow bandwidth. But for WSE2, you really have to go to very low angles, very small twist angles. At the same time, for the average DOS, the twist WSE2 stays low, but for the twist MoTE2, you have this very large DOS. So that's where the magic continuum comes from, right? So in basically from like roughly 3.5 or 4 degree right to 2 degree, we should all see this interaction-driven phenomena. And what's interesting is about the second band. So for the second band, you can see that that's a very narrow window, roughly around the 2 degree. You see a very large average DOS, right? And when we look at this band structure, again, you see this band structure I've emphasized earlier. First, the second, the third band, they all have Chern number equals to 1. So in the paper that Xiao has mentioned earlier from the Cornell group, for the two terminal conductance at a filling factor 2, 4, 6, they indeed see kind of a quantization, and which is consistent with our calculation here. But when you see this, right, and then naturally you would ask, wait a minute, 1, 1, 1, where else did you see that? Landau levels, not one Landau level, a set of Landau levels, 1, 2, 3, 4, right? So then okay, now do we have a higher Landau level physics here? But as I said earlier, to really mimic the Landau level, it's not just about you have multiple Chern band, you have flat band, or you have to really make sure that the geometry properties is also similar to the Landau level. So to do that, so we first did more calculations around the 2 degree, just to show you the band structure. You can see that for 1.89 degree and the 2 degree, you have 1, 2, 3, 4, even 4 band with Chern number equals to 1. That's actually truly amazing. But to understand this quantum geometry of those bands, what we have done is that we generalize the one-year functions directly from this 10,000 atom calculation. Because when you try to fit the band using the continuum model, it's not guaranteed that the quantum geometry can be captured. Okay, so you can see that those are the one-year function envelope. You can see it a little bit fuzzy because it's really have amplitude on each of the atoms. You can see that really interesting. One-year function is super extended in the real space because we have so many C equals 1 band. Okay, but how do we verify then indeed that those are a set of Landau level rather than just a collection of some random C equals 1 band? This is because an ideal Landau level first, of course, carries a number equals 1. But secondly, the integration of the quantum metric also equals to 2n plus 1, where n is the Landau level index. Okay, so it should be 1, 3, 5, 7. Now, if we look at the twist angle 2 degree, you see 4 Chern band. When we calculate this chi, it's 1.04, 3.09, 5.11, 7.53. So it's actually really closely follow this 1, 3, 5, 7. So this tells us that it's not just some random collection of those Chern band. Yeah, from top to bottom. Yeah. Okay. So once we've done that, so we basically performed a Hartree-Fock plus ED calculation. So the reason we did that is that of course, when you have a higher Landau level, your first idea is that, okay, let's look at whether it's a non-abelian state. So you want to really fill the second band at half filling. But because we don't have the resource to really do a proper 5/2 calculation, what we've done is that we've done the Hartree-Fock band calculation at the nu equals -2. Then we can project into the second band at a filling factor half. So this is really just a very preliminary result. We look at the many-body spectrum for both the 4x6 and the 5x6 lattice size. And this is shown here is the Landau level spectrum. And shown here is the ED spectrum from this Moray mini bands. You can see that they are very close to, they are very similar to each other. So we would call that a possibility that non-abelian state could be realized. Another very interesting thing is that if we don't do the Hartree-Fock calculation, we don't see those. It turns out that what the Hartree-Fock does is, again, is to flatten the barrier curvature under the quantum metric fluctuation. Okay, so this is some just numerical observations, and also there are a bunch of other groups also point out these same possibilities.
The Hartree-Fock?
The interaction is still the same interaction I mentioned earlier. Just yeah. So what are the open questions? So first is that even though, as I said, that is a very crude calculation, a lot of approximation involved. I guess there's a tendency we want to see what we want to see, but so the stability of this state against the band mixing needs further investigation. And more broadly, now we know, at least on a single particle level, we can confirm indeed you can realize this second Landau level. Now, is there a way how do we stabilize those non-abelian state? And then the next question is that, for us, really the project begin with we just want to try the new toys, this neural net stuff, but that's a surprise. But then is this multi-Landau level like bands bound to happen when you change the twist angle? We don't know. We want to believe it is true, but we don't know. And if it's true, what about, and is this unique to MoTE2, right? For WSE2, even though the band dispersion is actually very large, but whether, as you change twist angle, whether there's a magic angle, you can realize this higher Landau level physics. And finally, as I showed you earlier, is that this entire, band structure is really driven by the competition between piezoelectricity and ferroelectricity, which the former can be controlled by strain. So experimentally, if you can build a device that you can actively and accurately control the strain of the system, and whether that's kind of engineering opportunities, we can optimize the band geometry. So with that being said, so my time is up. I'll just leave the summary here. I want to thank my collaborators. So Chongwang has just joined Tsinghua, and Xiao Wei and Xiao Yu are the two postdocs, and also we benefit a lot of discussion with Professor Ying Ruan, Professor Ting Chao, and Xiao Dong. Thank you.
I was wondering whether once you've included Hartree-Fock effect, is like some generalized version of this McDonald model where you have some skyrmion like in real space. Can this still fit once you include Hartree-Fock effects?
Yeah, that's something we. So first, this McDonald's skyrmion model explanation really relies on you have to be able to project the other bands away, right? At a 3.89, that's possible because a pseudo spin never shrink. So that's the difference between a real skyrmion and our pseudo spin skyrmion. The length is not conserved. And we actually try some fitting. When we go to smaller twist angles, at one point, the pseudo spin just shrink to 0. So then there's a whole idea of adiabatic projection. Whether it works or not, it becomes problematic.
Thanks.
Yeah, thank you for the talk. Coming back to this idea from the very beginning with the perovskite that you showed. So you said you want ideally like a band that has a finite Chern number that is also flat, right?
Yeah.
I thought the nice thing about the Moray systems was kind of, the Chern number imposes like constrained to linearize or like to exponentially localize your Wannier functions. So I thought the nice thing about MoTE2 was basically, even though the Wannier orbitals are kind of extended, the real space distance is so large that you can still get like pretty flat band. So do you think you could ever be like in the regime where like the band is still flat enough and like an actual crystalline material?
Oh yeah, that's basically the whole point of that paper is that you can just, one thing is simply make the hopping smaller, as you said, right? But the other one is because of the d orbitals, if you think about dxy, dx squared minus y squared, they have very anisotropic shape. So when you consider they are hopping, the hopping itself is highly anisotropic. And that, even though the nominal t in front of it can be very large, but because of this anisotropy, the band can be made flat, as we showed. So the band stretch I showed there is just a very simple tight banding calculation. You put the d orbitals in there, the flat band just comes out.
In polygraphing, the interlayer heterostrain is something that matters. Is it also true here? So when you make a sample, the flakes, they are not rigid. So they can be heterostrain.
So that's actually exactly what we are talking about. That you mean like a external strain somehow built into the
Yes.
So that helps in a way that we actually have looked into this very very quick way that it helps to make the band flatter. If you can design it in a certain way, but in terms of the various effect on the topology, the piezo effect is the largest one.
Yeah, because in graphene, the heterostrain, well, something I'm not talking about relaxation. The heterostrain, it's gonna affect the many-body ordering.
You mean like you have like two layers, but you just stretch one layer.
The top layer stretch in this way, the bottom layer stretch in different or compressed. That's what I mean.
So that particular one, that's what we plan to do, because if you apply the heterostrain, that also affect your overall stream pattern, right? And then the piezoelectric effect kicks in. We don't know what's going to happen, but this is definitely one of the directions I think are worth looking into. Yeah, thanks.
So is there any reason why the interlayer hopping here is changed as a function of phase angle, but not in twist planar graphene?
So the interlayer hopping, in fact, doesn't change much as a twist angle. So remember that in graphene, because you have the time reversal inversion symmetry, right? So the Morley potential only appears in the off diagonal. That's your interlayer hopping. But here for the TMD system, because I already have a gap opening, so I have both the diagonal part, the intralayer Morley potential, and the off diagonal part, which is interlayer Morley potential. And all the effect, the piezo effect, is added the intralayer Morley potential, and they are the one that really change drastically as a twist angle change.
Thank you. Have you estimated if there is some sizable rush by spin orbit coupling, especially when you put a displacement field system, or is it suppressed because?
No, we haven't. But we now there's so many experiments to apply large gate voltage. I think we should.
So if there's no more question, let's thank Professor Lee.